Last time I talked about elimination, and then I wanted to be able to do that using matrices, and I used that to motivate my rule for matrix multiplication. And now I want to sort of try and put everything together, so really what we did in topics 3, 4, and 5, and have one specific example of trying to solve this problem AX equals B. So I have a square matrix A, an unknown vector X, and a right-hand side B. So where this comes from is a system of equations. So I want to try and solve this system of equations on the left here. So 2x1 plus 4x2 minus 2x3 equals 2, and so on. And I'm going to start by first writing this out in matrix notation. So I have so what I'm going to do is something kind of like the idea of place value when I want to write down a number. Just where these numbers are tells you a lot about what they mean. So for instance, I don't need to have the variables x3 in here anymore, because I know if I write it organized like this, where the third variable is always in the third column, the second variable is always in the second column, first variable is always in the first column, then it's clear what each of these numbers mean without having the little x there. So all that's important are the coefficients, and then these pluses and minuses are just going to show up as the sign of the number in the matrix. So I can represent this thing here as a coefficient matrix times this unknown vector x. The components of x are x1, x2, x3. And then I'm going to take the equalities, so the numbers on the right-hand side here, and put those in a vector and put that on the right-hand side over here. So that becomes my vector b. And now I want to be able to do elimination. I don't want to have to be carrying two things all the time. So really what I'm trying to do is introduce zeros in these elements that are below the diagonal. But I also need to be, and I want to do that by adding and subtracting multiples of one row from another. But I also have to keep in mind that every time I do one of those steps, that's going to have some effect on this right-hand side as well. So one approach to dealing with that is I can make something called an augmented matrix. And I'll call that A with a little prime next to it, so A prime. It's nothing to do with the derivative. It's just to distinguish it from A. And that's going to be the matrix formed by taking the coefficient matrix and binding this right-hand side vector B to it. And so that just looks like this. And so this is really all I need when I want to do elimination. I don't need these x's anymore, because just the position of these numbers in the matrix tells me what equation and what variable they correspond to. And now I'm going to do elimination on this augmented matrix A prime and see if I can't solve this system of linear equations. And so the strategy that I'm going to use, I want to do elimination, and I want to design each of my elimination steps to introduce a zero below the diagonal. So to get this into upper triangular form, the diagonal elements, so it gets a little bit trickier now when I have a rectangular, a non-square matrix. What does diagonal mean? Because I would sort of think it should go from top left to bottom right, but then it's going to miss a whole bunch of stuff. So the diagonal elements of a matrix are always the elements where the indices match. So this is the first row and the first column. This is the second row and the second column. And this is the third row and the third column. So that's the diagonal, regardless of how many rows and columns the matrix has. And what I want to do is choose pivots and then elimination steps to introduce a zero here, then here, and then here. And then once I have this as an upper triangular system, I can use the back substitution algorithm to solve this easily. And this time I want to do this with matrices. So I'm going to sort of go through this in all of its gory detail just one time, and hopefully it should be clear what this algorithm is trying to do. So I start out with my matrix A prime I guess I should highlight it down here. I have my matrix A prime here. And I want to find a pivot in the first row. So that's going to be, the definition of a pivot is the first non-zero value in a row. So if I start with the first row, if this value is not 0, then that's going to be my pivot. So in this case, it's a 2. It's not 0, so I choose it as my pivot, and I make it red. Then I'm going to design an elimination matrix that subtracts twice the first row from the second row. So in this case, what I look at is my pivot is 2. This is the row doing the elimination. This is the value I want to eliminate. So my multiplier was this 4 divided by the pivot, so I get a multiplier of 2. And then an elimination matrix says I have to take an identity matrix, and in the correct index below it, so in this case 2, 1, I take minus the multiplier, and I put that in there. And we know what this is supposed to do. This is supposed to subtract twice the first row from the second. So if you see what I ended up with over here, the first row stays the same. And then the second row, I have 4 minus 2. That's going to be equal to 0. And you always know you're going to get a 0 here because that's how you're choosing the multiplier. I'm choosing my multiplier specifically to make this one number 0. And then I have to sort of suffer the consequences of that decision with the rest of the matrix. So this 9, I'm taking this row minus twice the first row. So it'll be 9 minus 2 times 4, 9 minus 8, and that'll give me a 1. Then a negative 3 minus 2 times negative 2. So it gets a little tricky when you have minus signs in here. That's actually going to be minus 3 plus 4, so I end up with a 1 in this position. And then 8 minus 2 times 2 gives me 4. So that's my first elimination step, and it was represented by this matrix E1. And this isn't a standard notation. It's just something I kind of made up because this was getting a bit too complicated to keep following through. But essentially what I'm trying to do is I have my first elimination matrix will operate on my original augmented matrix and give me this matrix A1. So this is A1 on the right over here, and it's got this 0 where I wanted it. And then what I want to do is now come up with an elimination matrix E2 that's going to turn this value into a 0. So let's see how I do that. So I look at my matrix A1. Oops. My pivot is still a 2, and the number I want to get rid of is a negative 2. So I have a multiplier of negative 1, and that means I actually end up adding the adding the first row to the third row. So in the elimination matrix, this ends up being positive this time. And then I can either think of this as an elimination step like I did last time, or I could just, well, I probably wouldn't do it. I'd use a computer to do it. But you could just do the matrix multiplication, E2 times A1. And that's going to give you this matrix that I've called A2 on the right hand over here. And it has exactly what I wanted to happen. So I had this 0 here already. And now I've constructed an elimination to give me a 0 here. And to get this into upper triangular form, the last thing I need to do is get rid of this 1 here. And so I've already sort of used up this pivot, this 2 here, because everything below it is 0. So I'm happy with this column. So I'm going to switch to the next row. And in the second position, so the first number is a 0. So my definition of a pivot says first non-zero number in the row is going to be the pivot. So now it's this 1 that's going to be the pivot. So I want to find the pivot in the second row and then eliminate the values below it. So introduce zeros. So if I introduce a 0 below this 1, then I'll be finished. The matrix will be in upper triangular form. So it'll be an upper triangular system. So I'm going to do that with an elimination matrix E32. And this has a multiplier of 1. That's pretty easy because it's just 1 divided by 1. And that says my elimination matrix. So note that the 3, 2 here is telling me what position to put this multiplier in. And then because it's an elimination matrix, I want to subtract. So that's going to be minus the multiplier goes into the 3, 2 element. And otherwise, this matrix is just an identity matrix. So this matrix says I should subtract the second row from the third row. And so I can then either think of this as an elimination step, or I can just do the matrix multiplication E3 times A2. And that's going to give me my matrix A3. And it's done exactly what I wanted again. So this was a 1. I've eliminated it with this elimination matrix E3 and gotten myself an upper triangular matrix. And then just to be complete, so I picked this 2 in the first row as my first pivot. Once I'd eliminated the numbers below it, then I picked this element. That became my second pivot. And even though there's nothing left to do, there still is a pivot in the third row as well. So it's just the first non-zero number in the row becomes the pivot. And so in this case, we had 3 rows, and each row has a pivot. But I'll mention a little bit later, that's not always the case. So now it's easy to use back substitution to solve for the values of x1, x2, and x3. So here, this just means 4x3. So it's in the third column, the column that corresponds to x3. And then it's equal to 8, because this 8 over here is the vector I sort of bound on when I made the augmented matrix. So that tells me x3 has to be equal to 2. Then my second row tells me x2 plus x3 has to be equal to 4. So I already know what x3 is, so I plug that in and then solve for x2, and that tells me that x2 is also equal to 2. And then my top row tells me that 2x1 plus 4x2 minus 2x3 has to be equal to 2 as well. But I know x2 and x3, so I'll plug those values in, and then I find x1 has to be equal to -1. And so the solution x is equal to -1, 2, 2. So this is why it's called back substitution. If you notice, I ended up with these things in the backwards order. So I got 3, then 2, then 1. So the solution is x is the column vector, -1, 2, 2. And that solves also the original system, ax equals b. And then there's 2 caveats. And since I'm trying to just do a quick overview of linear algebra here, I'm not going to go into these kind of corner cases. But suppose when I started doing elimination, I could still have a perfectly valid equation that just happened to have a 0 on the x1 coefficient. And in that case, this 2 here would have been a 0. And I couldn't have used that value as a pivot, because I have to divide by my pivot. And obviously, I'm not going to be able to get anywhere if I have to divide by a 0. So sometimes, there's no particular reason why the columns have to be in any particular order. Why the rows have to be in any particular order. So you can move the rows around to get yourself out of this problem. So you would just pick a row that has a non-zero value here and use that as the first pivot. And so that's called making a row swap. So sometimes you have to swap rows during elimination. And then the other thing is sometimes there will be zeros that you just can't get rid of. You need a pivot, and there's only zeros. So for instance, if you had a row that was all zeros, that would have no pivot in it. And in that case, you say that the system is singular. And so either you will have an infinite number of solutions. So you could imagine just 2 equations for the same line. So one row is just a multiple of the other. Or you could have something like 0 times y has to equal 4, in which case there's no solution.